In Haskell, we love monads. We love monads for dealing with effects. But unfortunately, monads don't always give us, or monads in Haskell don't always give us the abstractions that we need. So for example, let's say we're working with some file handles. Haskell will accept this code as well-typed, right? Where if you open a file, you immediately close that file handle, and then try to write to it. But of course, it'll fail at runtime, and it's for a reason that is really statically wrong. It's something that it would be nice if our type checker could prevent. So let's see, how might we do this? Well, many of you in the audience might say, well, I would never write this code. I'm never going to open and close my file handles myself. I'm going to use something like with file, right, where you provide the file name and function that accesses the handle, but then at the end, with file closes the handle for you, right, and everything is good. And so then you can write some nice monadic code, like read write twice, or you can, right, you just read a character from a file and then you write it twice to that same file. Okay. But this abstraction actually can break. So if you call with file with return, then you get a reference to the file handle after it's already been closed, and you can do bad things with it. So I claim the abstraction that we really want is linearity. So if file handles are treated linearly, right, that means two things. One, linear data can't be duplicated. So once a file handle has been closed, all further references to it are just no longer in scope, so the type checker will prevent them. It'll also tell us that file handles can't be discarded. So by the end of the program, all your file handles, you must have closed them, and so you don't have to worry about garbage collection in that case. And so, for the past 30 years, linear types have proved to be the right abstraction for a lot of different kinds of effects. Things like I/O, things like mutable state, concurrency, things like quantum or reversible computing. I'm going to focus on I/O in this presentation. And I want these features in Haskell. And so today I'm going to be focusing on an embedding of linear domain-specific languages in Haskell. So this is something that we've been able to do for a few years, ever since there have been sufficient type-level features in Haskell, like multi-parameter type classes, type families, things like that. And we can write some programs in our EDSL that looks maybe something like this, right? We can open a file, and then we'll have some sort of let binding. And here I'm using higher order abstract syntax for let bindings and lambda abstraction. So let in takes in an expression that opens the file handle, and also a function, a Haskell function that takes in a linear reference to that file handle. And then we can read from that handle, and you get out both a new copy of that handle and also a character. So this process where you have to pass around your references to your linear data is pretty typical of linear languages. Okay. So then you can write that character to your file handle, and then you close the file handle, and everything is good. I would say this isn't super great to write. This isn't super elegant code. And this has been a persistent problem for working with linear types. So passing through these file handles is kind of annoying, but I think actually what's hard is dealing with the nonlinear data. So in this case, the characters. So question, what is the type of C? Sorry, not all those right C's are underlined. What is the type of C? Sort of the default might be, well, this is in our linear embedded language, so maybe it just has a linear type. But of course, that's not what we want. We want to be able to write that character twice and use it as many times as we want. So the typical answer in linear logic is to give it the type bang LCARB, so some linear type that is prefaced by a bang operation, which says that, well, this is a type of things that can be duplicated because there's nothing effectful about our characters, and we just want to be able to treat it. We just want to be able to use it regularly without worrying about linearity in our code. But this is a pretty hard problem, both from it's hard to provide a really nice interface for the user so that they know when they have to worry about linearity of their data. And for the language designer, this is also a kind of hard problem, and there have been certainly dozens of different approaches of how to deal with this bang type or how to deal with nonlinearity in linear languages. But in our setting, if I want to think about a linear language embedded in Haskell, what I really want is to be able to use Haskell characters, right? I want to be able to use library functions and just operate over them like normal. So this is what I want the type of characters to be. So this is the picture that I have in my head, right? I have Haskell on the one hand, and then I have a simple linear EDSL on the other hand that doesn't have to worry about any bang types or anything like that, right? Because it's able to harness Haskell data for its use by means of some interface, okay? So what is that interface? Well, as somebody who has studied linear logic before, I take a look at this picture and I say, hey, I know what that looks like. That looks like a particular model of linear logic called linear nonlinear logic, which exactly has this structure. The relationship between the linear world and the nonlinear world, in this case Haskell, is described by some categorical structure called an adjunction. And I'm not going to talk about what that means at all. But if you open up your category theory books and you learn a little bit about adjunctions, you can derive some conclusions. And here's the first one, which is that for any adjunction, if you take the composition in one of the directions, you get a monad. So we have a monad in Haskell, and I want to program with it. Seems like a good thing to do. And so a spoiler alert for the end of the talk, we're going to be able to use that monad to turn this code, which is kind of ugly and hard to reason about, and maybe I'm not quite sure how to implement it, into this code, where the user doesn't have to worry, actually doesn't have to access the linearity at all, but it's a property under the surface by providing a monadic interface to it. Okay. So how do we do this? So let's take a look at our linear EDSL. Okay. So the strategy, we're going to start off by defining some linear types, right? And so here tensor is the linear product, and lolly is the linear function type. And then we'll have maybe some file handles and some unit or something like that. We're going to use a final tagless encoding. And so we're going to define a type class that describes a typing judgment. That's this exp type. So an expression E of type x gamma tau means that E is a linear expression that uses variables in the typing context gamma, and it has the linear type tau. Okay. So we'll define some type of linear variables and some type of linear typing contexts, and so on. And the elements of this class are going to be ways of constructing our linear programs. So, for example, to do application, it's basically the standard application rule, except that we have to check that the variables used in E1 and E2 in the function and the argument are disjoint from each other. And so we check that disjointness condition by means of the type class merge, and that exactly encodes this relation on typing judgments, on typing context that we want. We can do the same thing for abstraction. So here we're using higher order abstract syntax, which means in order to construct a linear function, sigma lolly tau, we're going to give a Haskell function from expressions of type sigma to expressions of type tau. And the typing contexts exactly ensure that the expression of type tau that we get out of that function on the second to last line, uses the variables gamma in the target plus a fresh variable x. And so what we end up with is something like lambda and then arrow, x arrow e. Okay. So then we're going to continue on, and we'll define some interface for file handles, maybe open, read, which takes in a handle and gives you back a new reference to the handle and a character. And then write, which takes in a handle and also a character and gives you back a new reference to that handle, and close, etc. And then we can, with pairs and all these other constructions, we can try to write read, write twice, this running example. But there's a problem here. So these types don't actually line up. So what we get out of the read is a linear expression of type lower car, but we want to give just plain characters to the input to write. So in order to do that, we're going to look at this interface that we had between Haskell and our linear DSL. Okay. So this lower type lets you put Haskell data into the linear world. So we're going to extend our syntax of linear types to include lower, which takes as an argument a Haskell type. So type is the same as star. And like I said, we can take any data of type alpha and treat it as a linear expression of type lower alpha. Okay? And that linear expression doesn't use any linear variables. If we have an expression of type lower alpha, how do we get it out again? Well, you might think, well, maybe we can just reverse that. But of course, our linear language has maybe effects in it, right? Maybe we want to enforce something with our linearity. So this is not quite the type that we want. Instead, we want something, it's almost monadic, right? Given an expression of type lower alpha and a function that uses an alpha to construct another linear expression, then we can compose them together. Okay. And so our example is going to get out a lowered character from read, and then we'll use this composition, which I'm pronouncing let bang, to extract the actual character out of that lowered character. And then we can use that as the input to write. And there's no restrictions on how that character is used. Okay. So on the other side, this lift connective goes in the other direction. So given a linear expression of type tau, if that linear expression doesn't use any linear hypotheses, then just as in ordinary linear logic, we can promote it. So it can be duplicated into a nonlinear type. So here, lift tau is exactly a Haskell type, so it's unrestricted. Okay? And so I call this operation suspend, and I call its elimination force, because I think of these as suspended computations. So for example, if you open a file that has type handle with, and it uses no linear variables, and so you can suspend that computation, and then every time you force that computation, you'll get another handle to that same file, for example. Okay. Right, we said that this interface, which was inspired from the category theory, gives rise to a monad, which is lift of lower of alpha. Okay? We can give it a monad instance. It satisfies the monad laws. And what can we do with it? Okay? Well, one thing we can do with it, we can run it. So if you have lift of lower of alpha, we provide a way to actually execute that program, and it will maybe manipulate some file handles in I/O. So the output type is I/O alpha. That's a good thing to have. We can also write something like with file, which takes in the file name and takes in something that operates on file handles, but it operates linearly on file handles in this case. And then if it produces nonlinear data, so if it also produces a lower alpha, the interface at the end can be given the type lin alpha. And so the linearity monad is is like an interface to the outside world. So it hides the linearity from the end user in some way. And this definition is exactly what you'd expect. You open a file name, you force this operation, which manipulates file handles, and then you get out a new reference to that handle and you close it. So we can write our running example, read write twice, using with file. But it doesn't really look better, to be honest. It's, right, we're doing the exact same things, we just are not writing, we're just replacing open and close with one other line. So that's a little bit disappointing. But if we look at the type of with file again, and we look at this function that we're writing, it takes in a handle and it produces a handle. Hey, that's a state monad. It's just a linear state monad. So it's something new. So if we look at this picture again, right, we can imagine all sorts of linear monads on the linear language, including state or maybe or something like that. We can define a type class that describes these operations analogously with ordinary monads. We'll notice that a lot of the things that we've seen before, a lot of these file handle operations actually take this form, right? So write takes in a string and produces a monadic operation on file handles that gives you back a character. Read is a monadic operation on file handles that maybe gives you back a unit or something like that. And so read write twice, now we can write this in a bit more of a monadic style, right? So we say with file, and then we read, and then we get out a lowered character, and then we do let bang, and so on and so on. So maybe that's a little bit better, and maybe you could look at some rebindable do syntax or something like that, and it can be even smoother. But I'm actually going to go even further. So let's take another lesson from the category theory. Not only do these adjunctions give rise to monads, they also give rise to monad transformers. So for any, for any linear monad M, right, lift of M of lower is an ordinary Haskell monad, right, because on Haskell up there. And so we can give it a monad instance, and it satisfies the monad laws. And then these operations, read and write, if you stare again, they actually have this form, right? We're actually, since we're talking about nonlinear data, it's actually in this lifted state monad. Okay, so we can have read T and write T and so on, and then our with file operation has this form too, right? It takes in a lifted state transformation on file handles. And then our read write twice example is the argument is just a monadic computation on the state transformation. Sorry, on the state monad. And so that's exactly the story. In the paper, you'll find a lot more details about the implementation. We actually provide a pretty modular and extendable framework that can be used not just for file handles, but for a variety of different effects. We've implemented a number of examples, including mutable arrays, session types, quantum linear lambda calculus. And for anyone who has their favorite domain-specific linear language and would like to see it in Haskell maybe, I encourage you to check out our work and check out our framework and or talk to me, and I'd love to try to make that happen. In the paper, we also talk about a comparison to other models of linear logic. So we had the bang type previously, and all these different approaches for dealing with nonlinearity and linear logic. And in particular, there's this exciting proposal to integrate linear types into GHC itself, and which is a very different model of linear logic, and I'd love to sort of understand better how maybe this observation about monadic programming with the linearity monad can be useful in that setting. You can find our code on GitHub, and thank you very much. That is bang. That is the bang operation for ordinary linear logic. And you can write your sort of comonadic interface and give it a linear comonad type class or something like that in Haskell, and we do that in the implementation. Yeah, so that's a pretty cool consequence of the linear nonlinear model is that when you look at in the other direction, you get the ordinary bang operation.
Do you have a story for linear data? Like, can I have list of A along with list of A and make sure that that's a permutation?
So you can certainly define a linear data type of lists. In order to use Haskell lists, I don't really have a story for that. So that's one of the disadvantages of doing an EDSL, is that it's maybe not as easy to reuse. It's not as easy to reuse the Haskell data structures in the linear world, and so that's definitely could be a drawback. One possibility might be to use like something like template Haskell to fake that for the user.
So every junction will be derived from the monad. Every junction will also be derived from a recursion scheme. I wondered if you had thought about what happens when you start using the junction for that.
I don't know. Sorry, I'm not really familiar with how that would work, but I would love to hear more about it. Thank you.
I love this work on trying to make linearity actually useful to ordinary programmers, so thank you for that. Can I ask about extensibility, as you stressed extensibility at the end of your talk? So I can think of two axes which I wasn't sure about in your work. So that the L-type thing, that contained a special constructor for handle. So if I invent a new linear type that I want to work with, then do I have to change the framework? That's one. The other thing was, in your with file handle function, it looked as if the thing that it was wrapping could just work with file handles. I couldn't open a file, then do some database operation, launch a few missiles in ordinary I/O, and then be sure that I would go to close the file. So it seemed a bit sort of difficult to compose with my existing work. Is that fair? Do you know what to do about that?
So in the first case, in terms of, say, extending this to other domains, in the code, actually, this is simplified, what I showed you in the talk, but in the code, it is possible to extend L-type in your other file without modifying the core framework. In terms of combining this with, like, let's say, or other I/O transformations, by itself, I think that would not integrate that smoothly, but maybe you can define some linear type that just takes in some I/O transformation, and you can define its behavior to actually execute that I/O action. So you might be able to lift something in that way, but I don't have a very clear answer for you right now. But certainly you can extend your EDSL so that it includes some other interface to databases if you also want that to be linear in some way.
So all the code examples you gave were all multiplicative actives. So what about the additives?
The additives fit in perfectly well. So you can define these type classes, like higher order abstract syntax one, and the file handles one, and you can define one for the additives and just give it the rules. I would say I don't have a perfect type checking or type inference with these type classes that I've shown. There are other ways to design the type classes, such as seen in prior work, that can make that inference better. So in my framework, the additives may not always be typed correctly, but for in many examples that they will be, yeah.
So in your example where you read from a file, what if I need to read from 2 files?
Well, then you might define, so if you wanted to read from 2 files, then you might need to delve into the linearity a little bit more, right? So if you don't just want to use with file, then you can always sort of open up the linear world and open 2 file handles, and then you have 2 different H1 and H2 or something like that. And you might want to define your own abstraction on top of that. But yeah.
All right, well, no one more question.
So maybe just go back to slide 4. I think I remember on slide 4 there was an example of how you break the classical response. So I think one of the ways to solve the ST model is by using this special higher rank type. Is there any comparison to be made and disadvantages?
The higher ranked type? I'm not sure what you mean.
It uses something like that to distinguish the difference, so you cannot do this return in the model.
Oh, because it's got the type variable can't dictate the context of the ST.
Oh, right. Yeah, sorry.
You don't see how that is, so that could be a technique to prevent this from happening if such a thing were made for a file-based structure.
Sure, absolutely, yeah.
And I was just wondering, if you think about that, how does that compare to this technique when it comes to this specific file-based file handle application?
I think you could absolutely do that. And I would say there are many ways to solve the abstractions for all these different domains. But linear types are a very nice alternative abstraction. So I think there are other ways to solve these problems. And especially file handles are maybe sort of a toy example, because yeah, you could do this, but you sort of have to be malicious, and so most of us are okay with just using this abstraction. But yeah, you could definitely take that approach. Yeah.